Ademi. We also have Professor Chris Ashano. He's here with us. He was also once our LOC chairman, another veteran in these things. And Professor Solomon Yusuf, my brother, is also here with us. We recognize you, sir. We have quite around, and our LOC chair, he doesn't need any introduction, but we recognize you, Director Geophysics NGS Alhaji Abba Adamu Usman. I might be tempted to call him with his title, Marathon Fika. Okay, so we have someone on the screen. I'm sure you are all wondering. He's going to be the one delivering this packed workshop today. We have our brother. He's a Nigerian. I will go through his biography. We know he's a Nigerian. He has everything that can make him a Nigerian. Originally from Cameroon, but adopted by Nigeria. And working for South Africa now. So I'd like to introduce Dr. Tende Andogoma is here online with us, and he will be taking us through this process today. You're welcome. Before he starts, I would like to go through his profile before we formally invite him. But maybe before then, since we've made it a tradition, let's all rise for the national anthem. Okay, at count of three, we take the national anthem. 1, 2, 3. Nigeria, we hail thee, our own their native land. Though tribes and tongues may differ, in brotherhood we stand. Nigerians all are proud to serve our sovereign motherland. Thank you. Please, let's be seated. Okay, so I will go through a brief profile of our trainer, and so that we can get to meet him. Dr. Andogoma Waduku Tende is a research fellow at the University of Free State, South Africa, with over 8 years of interdisciplinary experience in mineral exploration, remote sensing, GIS, and earth science informatics. His research integrates satellite remote sensing, geospatial analysis, machine learning, and predictive modeling to address challenges in mineral prospectivity mapping, geothermal energy exploration, groundwater assessment, and environmental hazard mapping. He has extensive experience in university teaching, postgraduate supervision, and academic administration, having served as a lecturer at the Aliko Dangote University of Science and Technology, Nigeria, and currently as a researcher at the University of Free State. Dr. Tende has published extensively in high-impact international journals, including the Scientific Reports, All Geology Reviews, Remote Sensing, and Energy Geoscience. He serves as an associate editor and reviewer for several leading geoscience journals. His research focuses on advancing geospatial and artificial intelligence techniques to support sustainable national resource exploration, environmental management, and earth system decision making. Distinguished ladies and gentlemen, we hereby introduce to take us through the next hours of today, Dr. Tende. Not yet, not yet. Mm. Okay, so we are seeing your screen now. We are seeing your screen. We are seeing your screen very clearly.
Yes, I'm having. Let me just give me a moment. Okay. So the term mineral potential and mineral prospectivity are synonymous. They refer to each other, which is basically a concept of integrating data to identify favorable locations for mineralization. And this methodology explicitly uses statistical methods. There are various statistical methods used to integrate this data. These statistical methods can range from the use of concepts such as the fuzzy logic, weight of evidence, to the use of knowledge-driven methods, which is known as the analytical hierarchy procedure. And one major advantage of mineral prospectivity is it helps to identify, to reduce the cost of exploration and also time while improving exploration confidence. So implementing linear prospectivity helps to guide explorationists and improve their confidence and reliability of finding mineralization within a given area of interest. So in mineral prospectivity, we have two types. Sorry. Okay. So in mineral prospectivity, there's always what we know as exploration data recognition criteria. So what does it mean by exploration recognition criteria? Exploration recognition criteria often means for every geological data that is used or for every geospatial data that is used, part of that data has a kind of recognition or evidence for occurrence of mineralization. For example, if you're using structural data, like lineament density, zones of high lineament density are more likely to represent zones of favorability for mineralization occurrences, and the data-driven type, the model, and we have different kinds of knowledge-driven models. We have the fuzzy logic analytical hierarchy procedures, which are mainly used. A major advantage of the knowledge-driven is that it allows geology to actually trace or interpret the model based on understanding of the orb deposit processes that are associated with that mineralization. But major disadvantage of this knowledge-driven model is that it is subjective. That means that different geologists will have different ideas, or different researchers or different analysts will have different ideas towards implementing this model, which means that the result from one model might be distinct from one analyst, may be different from that of another. We also have data-driven prospectivity mapping. The data-driven prospectivity mapping relies solely on data, empirical data or evidential data. And in this case, you don't use the knowledge or experience or the expertise of the analyst. It tends to rely on evidence from the area of interest. And this evidence are usually occurrences of mineralization. So in the data-driven prospectivity mapping, the model simply looks at the evidence of mineralization and try to generate a pattern that is related to this evidence. And a common approach for the data-driven prospectivity mapping is the machine learning models, which we'll be talking later on. The machine learning models are data-driven or empirical models that use evidence from field data to dictate patterns that are related to mineralization. For the implementation of prospectivity models or mineral prospectivity mapping, we have challenges. There are different challenges associated with this implementation. And the most common challenge for implementing prospectivity mapping has to deal with incomplete or poor quality data. In many cases, when implementing prospectivity, we are faced with poor data availability. And as you all know, in GIS, it's either garbage in and garbage out. So when you give poor data, definitely you have a poor result. When you give reliable data, you have a more reliable result. Another common problem we have with prospectivity mapping is uneven distribution of known deposit types. So this causes some kind of biasness where we have maybe one section of the prospectivity model having a lot of mineralization, or one section of the study location having a lot of mineralization, and then the other sites little or no mineralization. So it causes some kind of bias, and prediction becomes a problem. The next common problem we'll be having with development of prospectivity map is the problem of multicollinearity. And multicollinearity deals with the situation where we have two data sets that are being imputed into the model, providing the same information. So in that case, this leads to the problem of redundancy, whereby the data or the presence or absence of any of this the model. And in this case, we have the problem of multicollinearity. And for machine learning models, we have the problem of overfitting and uncertainty. So overfitting, it presents a situation where the model tries to overtrain itself, try to configure itself to be so accurate, which is not usually the case. And while uncertainty has to deal with reliability. So when we have problems of overfitting and data uncertainty, it affects the accuracy and the reliability of the model. This makes it very difficult for analysts to actually assess the confidence associated with that model. And the last problem that has to do with predictive modeling, we know it has to do with difficulty in validating prediction in unexplored areas. So prediction validation becomes problematic because one, sometimes we may have lack of sufficient training data, which are reliable enough for validating these areas. In this training, we'll be looking at prospectivity, and this prospectivity model will be implemented using wide range of softwares. Different analysts have been able to use different software, but from my own experience, I've been able to use the AppMap software, which basically used to process the data, to integrate the data. We're using Envy. Envy is an image processing software that helps to process satellite data, identify geological structures and alteration pattern. I also use Oasis Montage. The Oasis Montage software will support geophysical data processing like AeroMark in radiometric data. I will use Excel. The Excel sheet will also help to manipulate the data. And Google Colab, the Google Colab mainly we use for machine learning implementation. And one thing I want to specifically draw to this study is the fact that we understand that many geologists are not data analysts. For example, they lack skills in Python programming or coding. But I've decided to develop this training to be based on the fact that you can basically code whether you know how to code or not. Thank God we have availability of AI tools that can assist in coding. So we'll be using AI tools to code and then implementing them within the Google Colab framework. So thank you. This is the first module I think I can present. So thank you. I'll look towards questioning. If no questioning, then we can move to the second module.
Thank you, Dr. Tende. I don't know. Are there any reactions, any question? If not, he can head to the next module. Oh. Okay, Mr. Abba.
Okay, thank you, Dr. Tende, for
Yes.
the first part of the lecture. What I just want to ask is,
Yes.
to what extent can a prospectivity mapping be successful when the various data sets are on different scales?
Okay.
You
Yes.
got
Do you have another question, or should I take that?
okay. Any other? Okay, we'll just take one more so that we can go straight to the next module. Your mic is with you. Please introduce yourself.
Thank you, Dr. Tetendi. My name is Dr. Oshisoya. I just want to ask the statistical analysis you mentioned, the fuzzy, the weight of evidence and code. I don't know. How do you go about it?
Yes.
Is it how do we get them calculated?
Thank you.
Oh,
Okay, so Dr. Tende, please go ahead and react.
Okay. Let me take one of Aba's question first. He talked about skill in prospectivity. Skill represents a very big degree of uncertainty when you talk about prospectivity. It induces uncertainty. And looking at research, skill has caused a lot of problems when you use data with different skill. For example, you're using variety of data. These data have different skill effects. And because they have different scale effect, they tend to affect the model in terms of the uncertainty, and definitely they have an impact on the output of and reliability of the model. So a good way of dealing with the scale problem is to resample the data. So what I mean by resampling means that you have to change the resolution of the data. So when you change the resolution of the data, or the spatial resolution of the data, you will sample it now to a common representative resolution that helps to reduce the amount of uncertainty that is associated with diverse data sets you'll be implementing in prospectivity. So for example, now we have different data sets. We have aeromagnetic, we have radiometric data, we have satellite data, we have lithological data. All of these data sets are acquired on different scales and possibly on different spatial resolution. So a best way of doing it is for us to, first of all, identify which is the most reliable resolution upon which prospectivity map can be developed. So when we identify the most important resolution, then we can resample this data set to a common scale and then implement it to actually reduce the degree of uncertainty that is associated with that data sets. A best way for us to identify scale is to look at the spacing of the mineralization to ensure that every mineral deposit is represented within a pixel. That is one way we can look at it. We calculate the spacing within the mineralization, what is known as the minimum distances. When you calculate the minimum distances, you can actually identify the most reliable scale to represent your data. But other researchers and organizations argue that using a defined scale, for example, like the Lancer scale of 30 meter, is favorable for integrating data sets. Thank you. Then, in terms of applying fuzzy logic, you said fuzzy logic, isn't it?
Yes.
Yes, fuzzy logic, weight of evidence, and analytical hierarchy procedure. Those are multi-criteria approaches. For example, fuzzy logic and AHP are multi-criteria, while the weight of evidence is the bivariate statistical methods. So bivariate weight of evidence is a bivariate method. For the fuzzy logic, for the and AHP, the procedure is one. You first of all identify the recognition criteria for each data set you're using. So for example, I want to map specific mineralization. And first thing I have to do is to first of all find out what is the relationship between this mineralization and your data set. Because these models are knowledge driven, which means that you have to understand the relationship between each of those data sets and the and the mineral deposit you are considering. For example, you want to map something like gold, common mineral that's of interest to most people. And what happens? We know that, okay, north-east, southwest lineaments are the structural control patterns for gold. High lineament zones represent shared zones, high porosity, alteration zones commonly associated with gold mineralization. So if you take a model like, for example, the AHP, in the AHP criteria or the AHP model, we have to do what's known as ranking, which means that zones that are more favorable give them higher weighting, and the zones that are less favorable, we give them lower rating. So first thing we do is, first of all, you prepare your spatial data. For example, if you have something like geological structures, you can develop what's known as linear link buffering, or you develop Euclidean distances to these lineaments. If you have something like density, you can develop a density map. Or if you have alterations, you can develop your alteration maps. The second thing is you have to classify or segregate your data into different classes. So probably you can select it because it's a knowledge-driven approach based on what you think. You can segregate it based on the number of classes you feel like you're interested in. So for example, I have the lineament density. I can separate it into 4 zones: low, very low, high, and very high. And for the very high, the high and the very high classes, I can decide to assign higher weightings to it. While the very low and the low classes, I can assign lower ratings to it. This same thing goes for the alteration data. Zones of high alterations within your area of interest, you assign higher weighting to them. And zones of lower alterations, you assign lower weighting to them. The same thing goes true for the host rock. So if you're looking at, you have the host rock, you understand the host rock, you can generate a buffer distance along from that host rock and classify them or segregate them into different classes, assigning weight of evidence into this data. So when you assign the weight of evidence for each of these evidential data sets, then you can simply integrate them by summing them up. When you sum them up, you will have the zones of high favorability popping up with higher values, while the zones of lower favorability will be popping up as lower values. So in that case, depending on whether you're working on ASP or the fuzzy logic, the concept of assigning these weights different.
Yeah.
For example, in the fuzzy logic is probabilistic, which means that from 0 to 1. But in the ASP, sometimes it applies what is known as percentile. So you apply percentile, but in applying the ASP model, you have to be careful because we have some computation you have to do. So basically, you have to sometimes use softwares to compute these weighted values for each of the classes within each evidential data. Or if you can't use softwares, the most common way for you to implement it, calculating the weight for every data, is to use Excel sheets. There are standard formulas and standard procedure for these computations.
Thank you.
I don't know if that's fair enough.
That's great. Thank you. So I think we can appreciate Doctor for the completion of the module 1. We'll go straight to your module 2, which is on machine learning application to mineral prospectivity mapping. Over to you, Doctor.
Okay. Thank you so much. Now we get into the concept of machine learning. And I know many people, when they hear about machine learning, they're a little bit frightened. I don't think machine learning is that hard. One of the basic things I always talk about machine learning is for you to understand what it actually entails. Basically, sorry, okay, let me just present here. So basically, machine learning is a pattern recognition. It's just a pattern recognition analysis. And what do I mean by pattern recognition? It means that machine learning is a kind of automation. It tries to look at patterns. When you're given a reference data, you try to look at patterns from a given set of inputs and try to predict an output from it. So it's a kind of reference data. And over the years, different machine learning models have been developed. There are a lot of machine learning models that have been developed, but I can just pick out a few, which is, first of all, the supervised learning. Unsupervised, then we have the semi-supervised, then we have the executable learning, then we have the deep learning models. So when we talk about supervised and unsupervised models, in terms of the supervised models, we have what is known as, they give you some kind of training data set. So they give some kind of evidence data or reference data upon which the model learns from it. So we can look at this supervised model like in the case of facial recognition. Now they're looking for face, maybe thumb printing. That's the common thing. You input your thumb print, and then it learns from it. Or let me see, if they want to get maybe study somebody's face, you input the person's face or from different angles. Then the model or the machine learns from that face. So anytime it sees that patterns, it highlights whether yes, it is that person or not. So for the supervised learning, we have some kind of training data set it gives into the model. While for the unsupervised learning, it tries to identify patterns that are related to that data set. And then it outputs these patterns. Semi-supervised uses both supervised and unsupervised learning models. Why the ensembled models is some kind of aggregate, some kind of model that's built on different aggregates, and then to enhance stability. For the deep learning is actually a multi-layer kind of learning model that helps to identify patterns based on how can I put it, like the neurons, like human brains, kind of mimic the human brains, using different iterations to identify patterns. So when we talk about machine learning in terms of mineral prospectivity mapping, we have two type of data set we look at. We have what's known as the target variables, and we have to have what's known as the predictor variables. So for the target variables, usually in prospectivity mapping or mineral potential mapping, target variables are usually known as the known mineral occurrences or verified mineral locations. So these are the data sets that are given to a model for it to look for the patterns that are similar to these known mineral occurrences. For this,
Sorry, doctor.
zones.
Can you be on full screen? Sorry, please.
Okay. Can you see my screen?
Yes, but
Okay, so
to
let's
be
wait.
on presentation.
Just give me a moment. Let me try and see. Okay, one minute. Okay, yeah,
Okay.
I'm on full. Okay,
There's
just
one.
a moment.
There's a small window there. I think it's from your side.
I need to close
Blocking your
this.
presentation. Okay.
Okay,
So that's okay. Thank you.
okay. So in terms of mineral prospectivity mapping, we have two main data types. We have the target variables. So the target variables are also known as the known mineral occurrences or the verified mineral locations. While the predictor variables are the various geological data sets that are used to deduce the patterns that are similar to already discovered zones of mineralization. So for us to implement machine learning, certain conditions must be met. And the first condition is we must have sufficient target data to facilitate this learning. When we have sufficient data sets, the next condition that must be met for machine learning is for us to segregate this data into two types. And this segregation of this data, we segregate the target variable into what is known as the training data, which is usually used to implement the machine learning model. And then we have the test data, which is used to validate it. From a common point, what is usually known is normally researchers recommend that, okay, use all the known mineral occurrences to train the model, and then you go to the field now, and then you do your validation. But if you can't go to the field, what you can do in terms of the target variables is to segregate them into the training data, which is used to train the model or to implement the model. And then you have the test data now. You can use to assess how well the training has been done. Then we have the predictor variables. In terms of predictor variables or exploration data sets, they consist of different geoscience data sets. And this geoscience data set can be geological. For example, we have lithological maps, structural maps. Those are geological data sets. We have geochemical data sets, which are represented by elemental abundances. We can have geophysics data sets. For the geophysics data sets, we have aeromagnetic data, we have gravity data set, we have radiometric data set. Then we have the remote sensing data set. The remote sensing data set also consists of satellite data, satellite imagery, which can either be multispectral or hyperspectral. Then we have the topographic data set, the digital elevation models, can also form part of the exploration variables for effective machine learning. Now, I talked about machine learning or the implementation of machine learning requiring a lot of data sets. Yes, it's true. Normally, when we use or when we implement machine learning, it requires a lot of data sets. But in the case of unsupervised learning, we don't require a lot of data set for the training because unsupervised learning learns from patterns. It deduces patterns internally within the data set. And these patterns are then interpreted by the analyst. Implementing machine learning has a lot of steps. And we have the first step, which is data acquisition, data harmonization. That's the first step for implementing machine learning. And for us to harmonize data, it's a common practice for us to what? To georeference all data sets into a common reference system and spatial resolution. So this helps to reduce ambiguity that's associated with the data, and also helps to what? To reduce the uncertainty that is associated with the data. The second process of processing or preparing data before implementing machine learning is what's known as clipping, is to restrict the data set into the defined study location. This means that if data A has an extensive area and data B is restricted, we can harmonize this data in such a way that all the data are overlying each other within the same boundaries. In the third phase is data cleaning. So in this phase now, we correct for errors that are associated with the data set. We identify errors, we identify duplicates that are associated with this data set. We remove them, we correct for these errors to ensure that these errors doesn't have a significant effect on the data. For example, you may be working on an area and then in one place you have the data may become problematic, maybe due to poor capturing and all those things. So you have to identify these zones where you have poor capturing and have to correct them before the implementation of machine learning models. And then the first stage is the normalization of the data sets. Normalization also can introduce uncertainty when it comes to machine learning. In some cases, we may have some variables having scale of 1:1000. Some of them having scales from 0 to 1. Some of them having scales from 0 to 0.1. So all these data set have to be normalized to a common variable, maybe from 0 to 1 or from 0 to 100. So you must implement them. And then the last stage of data acquisition is what's known as second data predictive variables, which means that after data have been normalized, we can generate secondary data. For example, if you have a set of geological faults or lineaments, we can then derive secondary data by developing either a lineament density map or distance to lineaments. So this process entails first process for correcting or facilitating the implementation of machine learning. And the second process or the second step we would do implementing machine learning is redundancy and multicollinearity evaluation. As I've said before, multicollinearity is often introduced into regression machine learning models. So it represents a situation where two data sets or two exploration data sets have the same impact on the model. So this means that if one of those data are eliminated from the model, the accuracy of the model doesn't change. And this introduces what is known as redundancy, because the presence of the two data doesn't really affect the quality of the model. So it doesn't affect the output of the model. So in this case, we have to assess for multicollinearity to ensure that every data that is introduced into the model is statistically independent. So there are different methods that can be used to assess the multicollinearity approach. And this method ranges from the Pearson correlation, which means that we can compare to see the relationship among these variables. And if two variables have very high correlation, some researchers will put it at 0.8. A correlation of 0.8 signifies the presence of multicollinearity between the two data sets. Another approaches that can use to assess for collinearity is by computing what is known as the variable inflation factor. The variable inflation factor will help to identify those data sets that have problems of collinearity or that have similarity. And in this case, when we have VIF values that are less than 5, it means the absence of collinearity. And if we have the VIF values that are above 5, it means the presence of collinearity. For the tolerance index is just an inverse of the variable inflation factor, which means that tolerance index and the variable inflation factors are very important parameters for assessing collinearity within any data sets. Then, to implement reliable machine learning models, we need to understand the relationship between the target data and the exploration data sets, which means that we have to find the relationship and see how well the exploration data set is capable of predicting the target. different methods have been implemented. The most common method is to use correlation. What is the relationship? So, in future selection methods for multicollinearity, future selection methods in machine learning, the analyst seeks to see how well the data will be able to predict the target. So different methods have been used to implement or to assess this relationship, and the common practice is those data that have a lower relationship are usually eliminated from the model because they will usually lead to they will lead to errors associated with the output model, or will use low prediction values or low prediction accuracy. So future filtration methods include the filter methods that ranks variables using statistical tests, mutual information, or correlation coefficient. We have the wrapper methods that iteratively evaluate future subsets via recursive future elimination methods or substantial selection. And then we have the embedded methods that leverage of intrinsic model penalties or tree-based impurity importance. So it kind of look at how important the data is to the target, and then it gives you an output. So in most cases, when we are preparing or when we are implementing machine learning, the training data becomes very important. In the training data set, we have two kinds of training data sets. Apart from what I said before, we have the training and test. In the training data set, we have what is known as the positive labels, and we have what is known as the negative labels. Normally, the positive labels represent known points of mineralizations or zones of mineral deposit occurrences or mining locations. The negative labels are some of artificially generated data sets that are unknown. So when we combine the positive and the negative labels in machine learning, they give us what is known as the target data. And it is important for analysts to generate the negative labels because to generate the negative labels or to generate the target data from the positive and the negative level, the analyst must ensure that the number of positive labels must be equal to the number of negative labels. The reason being that if these two data sets are not equal, it may lead to problems such as overfitting, which makes the model highly unreliable. So there are different ways the negative labels can be generated, while the positive labels is obtained from established data, field studies, and all these things. Negative labels are usually generated from the software using usually what's known as a constraint buffering approach. In software such as the ArcGIS, we have what's known as random point generation. So the negative labels can be generated randomly across the area of interest using software such as ArcGIS. Training data augmentation represents a scenario where there's insufficient data to actually implement machine learning. Usually, when we have insufficient data, analysts, researchers will point towards the use of multi-criteria approaches because multi-criteria is mostly data knowledge-driven approach. But in the case of sufficient data, machine learning models are usually recommended for mineral prospectivity mapping. But in poorly explored environment, where we have insufficient mining locations, insufficient known mineral occurrences, we may resolve to implement machine learning through the process of data augmentation. And the process of data augmentation is simply a process of increasing the number of training data set artificially in order to facilitate machine learning application. And in this case, there are different statistical methods or different spatial methods that have been proposed over time to implement or to augment this training data set. And for implementation of the training data set, the augmentation is mainly done on the positive levels, which is the number of mineral deposit locations. When augmentation is done on the number of mineral deposit locations, an equal number of random sampling, which is the negative levels, will then be generated to balance up this data. And data augmentation has proven to be highly effective approach for applying machine learning models. One common technique to improve the accuracy of machine learning models is to use model optimization. It's just a process of the model using its internal routine to actually identify the best configuration for the most reliable, the most accurate outputs. So the model tries to automatically use its routine to look for the best configuration. And there are different configurations or different kinds of model optimization that can be implemented. We have from the grid search, we have the random search and the Bayesian optimization. So when analysts introduce model optimization into machine learning models, it tends to improve the output or the quality or the reliability of the models. When machine learning models have been developed and statistical outputs have been defined, it is always important to assess how well these models have performed. What is the reliability of these models? A common approach for most analysts would be like to superimpose the non-mineral locations on the prospectivity map and then say, oh, most of my non-mineral locations fall within zones of high prospectivity. That may be right, but generally it's not right. So we need a statistical kind of approach to actually identify and validate accuracy of machine learning models. And different accuracy or different validation matrices have been proposed or have been used over time. And this ranges from the accuracy to the precision. We have the recall stroke sensitivity. We also have the F1 score. We have the most commonly used, which is the IOC AOC approach method for validation. And then we have the coherence approach, which deals with agreement by chance. So when we've done that, we've done the prediction, we have a very good accuracy. The next step will be to predict the probability of mineralization for each pixels, generate a prospectivity map, and then classify the prospectivity model. So we classify it in terms of the values or higher probability values insinuate generally higher confidence, and lower probability values insinuate a lower confidence of exploration targeting. And when we do that, to improve the confidence, we usually employ what is known as uncertainty. Uncertainty analysis deals with how reliable different parameters within the data set or different methodologies within the data set, how reliable were they, what contribution, what did each of these data sets contribute, or how did these models work towards the output models. And we have uncertainty from different sources when it comes to machine learning. Uncertainty can be as a result of the data quality, it can be as a result of the methodology used, it can be as a result of the strategic value, it can be as a result of the interval of prediction. So uncertainty is not really restricted to any one parameter. Uncertainty associated with machine learning models can arise from any of the processing of the any of the steps associated with the processing of the model. Uncertainty can arise from the data sources. What type of data we imputed into the model? What were the quality of the data? What was the spatial resolution? Uncertainty analysis of the model can be attributed to the method used. In some models being implemented, we can have higher uncertainty. Other models can have low uncertainty. So uncertainty doesn't really have to deal with one particular aspect. It deals with the different contributing factors that led to the output. And in the summary, uncertainty estimates the error. It estimates the error that is commonly associated with that model. So error sources that are associated. So tends to look at where the different error sources came from and trying to quantify it across the data set. So thank you so much. So before I go to the next one, I would like to take questions.
Okay, so thank you so much, Dr. Tende. Do we have questions? We can take two. Um, if we don't have, then he can proceed. Any questions? Okay, so doctor, I think we are okay. So let's fire on.
Okay. So thank you so much. The next step we look at is mineral system approach to mineral prospectivity mapping. And usually I look at mineral system approach as the foundation for mineral prospectivity mapping. Why do I look at it as a foundation? Because it gives you the reliability, or gives you it's mainly a decision making for selecting data sets.
Okay, on presentation mode. Sorry, please.
Okay, thank you.
Thank you.
Mineral system approach. So what is a mineral system approach? So it's mainly identify where the geological conditions are required for mineralization. So we all know that mineral deposits are formed by a variety of different processes and under different conditions. And understanding these different processes and these different conditions under which this mineral deposit will form facilitates selection of different data sets that can be inputs into the prospectivity model. So we have, in terms of the mineral system approach, we have different data sets. They can be ranked based on the sources, the transport mechanism. So they can be ranked based on the source, transport mechanism, pathway, traps, and preservation conditions. And when you understand the mineralization and you understand these various components of the mineral system, it facilitates what are the sources? Where did the metals originate from? Tells us the source. Number two, it tells us the energy drivers, the process that generated fluids and moves it. So these energy drivers can be heat sources. For example, if you're dealing with mineralization that was formed through hydrothermal processes, probably there must be a heat source that actually facilitated migration of these fluids. The transport mechanism tells us how did it move? How did this fluid move? And the pathway, what directionality did this mineralizing fluid follow? And then when they moved, we have what is known as a depositional trap. So these are conditions that causes mineralization to precipitate. And the last one, we have preservation, because if we have the trap and then these mineral deposits are not preserved, there will be no mineralization. So these different components can be identified from the different exploration data sets that will be used into mineral prospectivity, and identifying what data set belongs to which component in mineral prospectivity is essential for building reliable predictive models. Hello?
Yes, we can hear you.
Okay, so now for you to move from mineral prospectivity to the concept of mineral system, we need to first of all identify the mineral system of the mineralization under investigation. So you identify the mineralization, you identify the different components of that system, from the trap, from the source, and all those things. Then you identify the critical geological processes that were associated with each of these processes. When you identify them, the next step is to define the exploration criteria. So for example, you define what is the exploration criteria for each of them. if, for example, you're dealing with a hydrothermal alteration data set, and we're looking at satellite data that shows this, then we select the most to generate the evidential data. The evidential data are actually exploration data sets, special exploration data set. For example, we have data sets such as hydrothermal alteration that's derived from satellite data, or we have a magnetic anomaly data or gravity data. Those are the evidential data sets. They actually present evidence of mineralization. And after you've generated evidential data sets, we integrate these data sets using any statistical methods, whether it's machine learning or multi-criteria methods. And when these data are integrated, then we produce a prospectivity map. And so this is how we translate from the concept of mineral system, magmatic or hydrothermal system, metalliferous sedimentary units, geochemical anomalies, radiometric and geophysical signatures. Those are the potential evidence for the source and meta fertility. Then, in terms of the transport pathway or the fluid transport and pathway, we have mainly shear zones, faults, fractures, geological contacts, permeable lithologies, measure lineaments. They form the fluid and the transport components of the mineral system.
We lost you momentarily, so I think from tectonic stability, we didn't get your comments on that.
Okay, on this slide.
Yes. The previous.
Okay, so what I'm saying is that
the previous slide.
Yes. Okay. This is okay. This okay.
The network was a little bit bad for us down here.
Okay, I'll take it back from the source and meta fertility. So when building can you hear me?
Yes, we can. Thank you.
Okay, so when building a prospectivity map, it's important for you to identify the different components of mineral system that ranges from fertility to the source, fertility, or what's known as a heat source, to to transport system, depositional preservation. So in terms of the fertility heat source, the potential evidence are fertile intrusive rocks, magmatic or hydrothermal systems, metalliferous sedimentary units. Can you hear me?
We can hear you. We can hear you.
Okay.
Go ahead.
So we have geochemical anomalies. So sometimes when we do from geochemical data, we can actually point out the source. We have radiometric and geophysical signatures. Those are potential evidence for source meta fertility. Then we have what's known as the transport pathway or fluid transport and pathway. Those are those components of the mineral system that's in charge of transporting the mineralizing fluids. And important considerations should be fault, fractures, shear zones, geological context, permeable lithology, measure lineaments. Those are the very important components that represent fluid transport pathways. Then we have the deposition and trap environment. So in this case, we have zones of chemical reactions, we have changes in temperature and pressure, we have fluid mixing, changing in pH or oxidation state, permeability contrast, reactive host rock. All of these components represent the depositional environment, which means the zones where we have precipitation and mineralization formation. Then we have preservation, because after the other components have been done, if there's no preservation, there can't be any mineralization. So in the preservation, we have the barrier and uplift history, we have erosion, we have fault reactivation, we have weathering, we have the tectonic stability of the area, we have the geological architecture. So all of these components will represent preservation and geological architecture, which helps to what? To keep the mineral deposit intact over time. In this slide, I'll be talking about the various components, mineral prospectivity components, and how they relate to the mineral system components. So in the case of one, we have the source. So usually the source, we can consider the geology, we can consider the geochemistry data, we can consider geophysical data. Geological data, geochemistry, or geophysical data can help point towards the source. For example, lithological units can tell us the source where this mineralizing fluids were generated. And this source can be deduced from geochemical data and also from the geophysical data. We can actually deduce them, which means that we can use either geological data, a geochemical data, or geophysical data to actually identify the source of this mineralization fluid. The next thing is the energy driver. So when the source, we have the source, there must be an energy that drives it through a pathway. So this mineralization driver, sometimes we can have intrusions, we can have tectonic setting, we can have heat flow. So in some cases, when you have intrusions, that provide the necessary heat for the necessary heat for mobility or the necessary heat sorry, we have heat sources that provide the necessary heat sources for mineralization, fluid flow, migration. They represent the energy source. Then we have the transport component, which is represented by fractures, which is represented by faults or by shear zones. And then we have the pathways, which can either be lineaments or lineament intersections. So lineaments and faults as one and the same thing. Then we have the traps. So the host rock is usually the traps. Lithological contacts are traps or alteration zones that are derived from satellite data can form the trap components of a mineral system. And then we have the preservation mechanism, which is the geological architecture, erosion, history, and all those things can help guide in terms of the preservation. So these are the various ways we can relate the mineral components or the mineral system components to the mineral prospectivity evidential data sets. And without a clear understanding of the mineral evidential data sets and how they relate to mineral system components, it will be difficult for us to actually build confidence prospectivity models. It is important for us to identify what data set relates to each of them. As a note of concern, sometimes we may not have all data sets for the different components, but the more data set you have, the more reliable your model becomes. And what are the key advantages and takeaway when it comes to this? So the first thing is that it provides a process-based approach to exploration. When we are using the mineral system approach to build prospectivity models, it actually builds a process-based approach, which means that every deposit is unique because every deposit has its own mineral components. And when we identify these components, it means that we are able to translate the ore-forming processes into reliable prospectivity models, which improves the confidence. So it reduces reliance on individual exploration indicators. So when we have the concept of the minerals system approach, we know that every data set has its own contribution into the model based on the mineral system. So every data has the way it relates and the way it relates from the mineral system into the output model. And the third thing we have is it integrates geological, geochemical data, geophysical, and remote sensing evidential data. Yes, when we know how to relate the when we know how to relate the mineral system into prospectivity mapping, we know which data set belongs to which component. So we are able to integrate this data effectively for a more reliable output. And then it supports systematic target generation over large areas. Because you understand how the mineral system works, we are able to identify what section of that data is reliable or what section of the data actually supports evidence for mineralization and which or actually has a higher confidence for mineralization. What section has a low confidence for mineralization. This facilitates identification of target zones over large areas, improving confidence, improving the reliability of the model. And the last thing is it's compatible with statistical modeling and machine learning. So the mineral system approach facilitates statistical modeling, it facilitates application of machine learning, it facilitates data integration because it gives you a general idea on how this mineral deposit was formed and what processes were responsible for its formation. So understanding the mineral systems helps to identify, to select which data is reliable and which data is non-reliable. And this facilitates the processing and the confidence, the output of mineral prospectivity models. So I think that's all I have to talk about mineral system approach with respect to prospectivity mapping. I would like to take questions. Um, I think from here we'll be having a break and then we'll come back, start the training.
Thank you so much, Dr. Tende. Thank you. Do we have questions? Because we'll have a health break, then we'll start the training proper. LOCJ.
I think we should have more questions here. Professor Smart, you have to ask questions. I can see you here writing a lot. Okay. Thank you, Dr. Tende.
Yes.
Okay. Thank you, Dr. Tende.
Yes, sir.
My own may be a comment, but
Okay.
there will be a question. Now, I will
Okay.
start with the comment. You see,
Yes.
in this part of the country, one of the
Yes.
issues that really um, make it not possible for Nigeria to define her mineral resources or deposit
Yes.
is the lack of understanding of our mineral systems. You realize that because we do not have many of large scale exploration, like
Yes.
you have suggested. So we have very few comprehensive or complete exploration where you will have all the different layers: geophysics, geology, geochemistry, and so on and so forth. So,
Yes.
I will give you an example. Nigeria, most of the report for gold, for instance,
Yes.
so most of the report you find, you only see that we are reporting orogenic gold, that within the sheet
Yes.
belt. Now, it's of recent that we begin to now report on granite hosted gold. Now, but then my belief is that even other deposits like the IOGC and so on may be available in the
Yes.
country, but we have very little exploration to report on that.
Yes.
So,
Yes.
and so I begin to wonder now, if I look at our geological neighbors, like the Brazil, because we share the
Yes.
same Gondwana crater and so on. So if Brazil will have some of these bigger deposits, scan deposit and so
Yes.
on, then I wonder why Nigeria cannot have that. So since we do not have enough large-scale exploration, where can artificial intelligence be leveraged to help us identify some of these deposits? Thank you.
Sorry.
Thank you. Thank you. I say you are in South Africa, and South Africa has a lot of gold deposits.
Yes.
Maybe, uh, and also based on your experience, I believe you must have used
Yes.
you might have used what you've just taught us now to
Yes.
prospect for this gold.
Yes.
How
Yes.
how successful were you in using the machine learning approach to locate some of these gold deposits in South Africa? Thank you.
Okay, thank you. You can respond now, please.
Okay. Let me start with this question. In South Africa, my research in South Africa, I'm not working on gold. I'm basically working on lithium in an area known as Northern Cape province of South Africa. Um, I work on lithium, and the initial part of my research, I used the fuzzy logic model, which I've published in the All Geology Review journal. And the later phase of my research, I used I'm using hyperspectral imaging to map alteration associated with these lithium deposits in the Northern Cape, what is known as in the Mapala Metamorphic Province. So I have not used machine learning, but I've tried machine learning in other parts of Nigeria and in Cameroon. I'm currently using it now to explore mineralization in Northern Cameroon, using augmented data because what I know about mineralization in this part of the world in terms of West and Central Africa, there's little or no evidential data for us to sufficiently train mineralization. However, there are papers where other authors have applied machine learning, and I can tell you, yeah, there's confidence there. The reliability is there, and new targets have been identified within the prospectivity models. So that is that.
Thank you. Thank you.
For the case of Nigeria, I think it's Dr. Alu asked me this question where we have more deposits in South America, and then we have less deposits in Nigeria. The first thing is I believe that mineral deposit systems are unique. For example, if you have the orogenic gold mineralization, their systems are unique, or identical or similar. So, hello?
Go ahead.
Can you hear?
Yes, we can hear you.
Yes. So, in Nigeria, where we have limited deposits, currently I'm trying to develop augmented data or an augmented machine learning approach, which means that I make use of the limited data sets and then try to generalize them and then apply machine learning, which I think to a large extent have been successful because when I compare my models to the traditional knowledge driven, I see a lot of similarities. But in that case, I think researchers or geologists now are developing what is known as transfer learning. People in AI will tell you that there's a concept known as transfer learning, which means that you could actually pick information from one section of the world and transfer that aspect through machine learning into another area that are similar. So if in the case where you have similar geological terrain, you could actually develop machine learning from one aspect and then use that same pattern applying to your data here, maybe in another section of the world, to identify or maybe to generate your targets. I think that's what's currently being done now. I think one of my colleagues is trying to do that also, and I've not gone into transfer learning, but I have the concept of doing transfer learning. I think that's the best way we can apply machine learning with confidence, since we have limited data and we have areas that have been overexplored, so we can do transfer learning. You must not go to Brazil to bring information. You can look for two environments within Nigeria. For example, the Middle Benue Trough. They have similarity in terms of the geological settings and all those things. And probably we can say that the Middle Benue Trough has been overexplored, for example, lead zinc mineralization. And then...
Yes, so man in English, Abi.
No, it is his father that is the professor. Hello?
His father is
Hello?
Just, it's okay. It's okay now. Go ahead, doctor.
I had a noise. So we can have the aspect of transfer learning. That's an aspect that I will encourage researchers to develop, where we have two environments that are geologically similar. Then one area has been overexploited. So we could use information or deduce information from the area that has been overexploited and transfer that pattern to the underexplored region. And then we can validate it now with those mineralizations or the lithium mineralizations that are there to see if there's any similarities. So that can work when you employ machine learning in Poland and the squad zone. In that case, if that doesn't work, then you can use augmented system approach where you have to augment the mineralization types to deduce or to apply your machine learning.
Okay. Thank you.
Yes.
So they just want to know if there are cases of transfer learning that has been implemented. You have anyone or published?
For the moment, I think a colleague of mine is developing an aspect of transfer learning. Transfer learning has been applied to other aspects of machine learning, not to mineral prospectivity. It's a very interesting area for research. It's a very interesting area for research whereby researchers can actually use it. The concept has been proven to other aspects of machine learning. For example, I think facial recognition or something like that. But in mineral prospectivity, I think it's a new aspect. Researchers are still trying to employ transfer learning.
Okay, thank you. Please let's appreciate Dr. Tende. Thank you for completing this second module. We'll be having a break, a health break for 10 minutes, and we'll reconvene by 11:45. I hope that's okay by you, Dr. Tende.
Yes, it's fine. It's
Okay,
fine. Thank you.
okay, so we'll see you 11:45. Thank you.
Okay, sir. No problem. Thank you.
Thank you.
Yes.
Okay, please, can we settle down? Um, Ushers, please help us tell those outside to come back to the hall so we can start. Dr. Sarah, can you help me tell them we want to start? Those outside. Please, let's settle down. We want to start now. Check, check. Okay, so Dr. Tende, can you hear me now?
Yes, I can hear you.
Okay, so we're about starting. Just give us like 2 minutes and we'll start.
No problem.
Okay, thank you.
Okay.
Okay, so we are back from the health break. And thank you, everyone, for coming back and for joining us for the next sessions of this workshop. Dr. Tende has been able to take us through about 3 modules from the morning to this time. On module 1, where we dealt with mineral prospectivity mapping concepts and applications. He has also gone through machine learning application to mineral prospectivity mapping. And lastly, before our health break, we looked at the mineral systems approach to mineral prospectivity. We are heading into the next stage, which is the exploration, data preparation, data generation, projection, resolutions. Before we go into that, I would like to introduce, he wasn't here when we started, even though we had his spirit with us. Please recognize in our midst the president of Nigerian Association of Exploration Geophysicists, Mr. Akin George. He's here with us. Thank you, sir. We recognize your presence, sir. So, Dr. Tende, we are back to you.
Okay.
Over to you now.
All right. Thank you so much. I think we'll start with the practical session on how to build reliable prospectivity models. Before going to building the reliable prospectivity model, I would like to share the area I've chosen. I think, well, some people may query me for this area, but I had a lot of troubles choosing this area because of lack of evidential data. So I had to struggle to pick up an area I think we could actually build prospectivity. So I tried to use Kuje. Kuje has a fairly it's fairly explored, not really explored, but I think from the mineral deposit map of Nigeria I've seen, Kuje has some deposits locations which we can use to as a practical example. In this study, we'll be applying machine learning assisted predictive modeling. And because Kuje is fairly underexplored, so we'll be using the machine learning models that has reliability for insufficient data, the random forest. There are different machine learning models, and application of different machine learning models depends on the quality of the data you have. So because we have insufficient training data set, and the random forest has been proven to work well even with insufficient data. So we'll try and use the random forest to illustrate how it works with this model. Other models can similarly be implemented based on availability of data. The concept is the same, but the model types differs based on the area location and the data type under consideration. So that's that. For us to implement machine learning model in this area, in Kuje area in North Central Nigeria, we first have to start by identifying or relating mineral systems for these different data sets. We have different data sets that we have to use to develop the mineral system. We have the lithological data, we have the structural data, we have the remote sensing data, we have the geophysical data. Unfortunately, I couldn't get the geochemical data, but as we all know, in prospectivity mapping, the number of data you input into the model is undefined. So we could use any unspecific number of data sets into the model. So for this study, we'll be using lithological data sets. It is important we talk about the source of the.
So, doctor, please get that on presentation mode. Sorry for that.
Okay. I'm so sorry about this. Okay. So, in this study, I'll try to apply machine learning assisted predictive mapping for gold deposit in Kuje, which is close to Abuja, North Central Nigeria, and different machine learning models do exist. Selecting the best machine learning model for any project is dependent on a number of factors. And one of those factors is the availability of quality data, especially training data sets. And because Kuje has fairly limited number of training data, so we're going to use a machine learning model that works well with limited data sets or limited training data sets. And this is the random forest model. So the random forest model has been proven in mineral prospectivity to work well with low insufficient training data sets. And the option we could actually use is to use augmented data sets. I think in North Central Nigeria, I'm trying to use augmented data set. We are working towards using augmented data sets to develop prospectivity model.
Sorry, doctor, are you sharing the screen? We can.
Yes. Oh, you can see my screen.
No, we can't. And it just it disappeared.
Okay, let me share it again. Okay. Can you see the screen now?
Yeah. Yes,
Okay.
we can see that is on presentation mode now. We
Okay.
can see it.
Yes. So
So you
I
check
was
your own
talking
system
about
media.
the location I selected for machine learning, and I was saying also that
Just a
in
minute.
machine learning,
Okay. Okay,
yes,
just a minute.
your choice of machine learning depends on so many factors. One, target data, the amount of evidential data you have to use as the target matters. So machine learning models like the deep learning uses a lot of target data. Obviously, in an area where you have limited target data, deep learning models won't work well. So in that case, we have to resolve to either using machine learning models that works well with limited target data, or we do data augmentation. At the moment, I'm trying to use data augmentation in a project in north central Nigeria to map lazy mineralization. So for the moment, I'm trying to develop that augmentation, data augmentation for that project. But in this case, I will not be using data augmentation. I'll be using random forest, which is known to work well even when we have limited training data size. So I will apply it to Kuje. There's gold occurrences have been reported in Kuje, and I had access to the so I found out, okay, it has fairly number of mineralized sites. So that's what I'm going to be using here. In this section, I'm going to be as detailed as possible to enable everybody to carry along on how machine learning is implemented. From the software routine, I'll talk about the software routine, I'll talk about data sources and everything, and then I will go into the implementation. So basically, the data I have is the raw data set, primary data set that was acquired from the field. And I have variety of data sets. I have from the lithological data, which is established geological map for North Central Nigeria, published by the Geological Survey. So this lithological data set is published by the Geological Survey. I will be using structural data sets. So the structural data sets will come in the form of lineaments. I have not yet derived the structural data set, so I have two ways of getting it. Either I use a map with the structural data set, or I generate it from digital elevation model. So from the lineament generation, I will derive the lineament density and the distance to lineament, favorable lineaments, so the lineaments that are actually controlling mineralization. So I can generate two data sets from the structural data. And then I have the remote sensing data. For the remote sensing data, we're using Landsat 8 data. And for the Landsat 8 data, I'll generate clay, ferric, and ferrous iron alterations. These alterations types are commonly associated with bone mineralization in north central Nigeria. And then for the geophysical data sets, I'll generate two. I'll generate the analytical signal data. And then I'll also generate the potassium and thorium ratio. Sorry, not potassium and thorium. I'll prefer using uranium and thorium data, and I'll provide reasons when I come to those data sets. I'll provide reasons why I prefer using a uranium and thorium data set. So for us to build prospectivity map for Kuje, the first thing we need to do is to understand what mineral components do each of these data sets represent. For example, lithology. What mineral components do lithological factors represent? What lineament components do mineral components, lineament density and lineament density distance represent? What components are represented by clay, ferric, ferrous iron alteration, and then what component are represented by the analytical signal, the magnetic data, and the uranium and thorium ratio. So I'll be specifying it over time, and I will also be identifying the component as I work. So We can start with the preparation of the first data set, which is the lithological data. I hope you have time because I'm going to implement digitization. I'm sorry. So we have lithological data. So we start by preparing lithological data. So I'm taking it from the lithological data. So the first thing we have is we have the ArcGIS interface. So for the ArcGIS interface, we have to create a database. So you can create a database within the area where you want to save it on your computer. So I will start by implementing it. So I will create a database so that I don't lose access to my files. So I can just goal prediction. So I can put Kuje. So I have that. So that's the first thing I have. Then I will save the database. So I will create I will create a database. So we can come to catalog. So when you come to catalog, so we can create a database for catalog. So first thing you do is you create your database. So you can create a file database. Kuje. Whole mapping. So I will translate my file or my session I have on ArcGIS into the Kuje goal mapping. So that all data I'm saving from this session will save into that database. So first of all, I create the database and then I put it. So I ensure that everything is safe here. So I have it there. So next step, I come back here and I save. So I can save my file. Yeah, so once this is done, I've secured the database, or I've gotten the database ready. So the first thing is I want to prepare lithological data. The lithological data I have is obtained from the Geological Survey of Nigeria. So I have it here. So this is it. It's derived in PDF format. So this is the PDF format of the lithological data I have. So the best thing I can do is to georeference it and then extract the area. But as PDF is already georeferenced, so I can import it directly into ArcGIS. So
hello, Dr. Tende. Dr. Tende.
Yes. Yes, sir.
Yes. May I know if we can get a small tutorial from you on the software? Yes, a tip, like a guide, so that we can concentrate and not care to take detailed notes.
Sorry, it's echoing.
Yeah.
Okay, I can hear
Yeah.
you now.
So what I was saying is that can you give us a small tutorial tips at the end of the lecture so that we can just pay attention to you, not caring to take detailed notes on the.
No problem. I can generate that at the end of the lecture. I can generate that and share.
Exactly. Thank you. Thank you.
Maybe a routine.
Okay. Thank you so
Yes, I
much.
can
Thank you.
generate that and share it at the end of the day on how to go about it.
Okay.
But
Thank you.
equally, I think it will be interesting if this tutorial, this lecture can be recorded, so that anybody who is interested
I
can
think
follow
it's be recorded. It's be recorded. It's be recorded.
Yes, I
Thank
think
you.
that would be the best thing.
Thank you so much. Thank you.
Okay.
So go ahead,
Okay.
please.
So yes. So the first step I'm trying to generate is the lithological data. So sorry. So lithological data is the first thing. Before I generated the lithological data, I tried to prepare my database for saving the various shape files or the various files I have. So I will import the lithology. So we have the lithology. So this is the lithology. I will import it into the ArcGIS software. So that's the map for North Central Nigeria. Then I will import the boundary. That pertains to Kuje. So this is where Kuje falls. Okay. Okay. So I have this. So now, since I have this as the boundary, I will definitely save this shape file into lithology before digitizing. So what I will do now is I will save this boundary file back into my lithological file, but now retitling it as lithological data. So I add it into my shapefile. Then I have it here, so I can enhance it, maybe by improving the boundaries so that it could be well visible. I have it here, so I'll use the editing tool to digitize the various components of this data. So basically I select it and then
Hello, Dr. Tende.
yes, sir, I can hear you.
Okay, are you with us? Because
Yes, sorry, I'm just trying to digitize the
okay,
various lithological units.
okay,
As
okay,
promised, I want to take everything from the basics.
okay, okay.
So it's time consuming. You guys have to excuse me, but I think that's the best way out of learning machine learning. You have to understand from the basic into the more complex issues. So,
Absolutely.
so that's how I feel. Yes, yes. So we have to go from preparation of every data set to data integration, to testing for collinearity, and then before doing our data integration. So everything is relevant. If I miss any of these steps, then people may begin to have doubts as in how some of these data were processed. So I'm trying to digitize it. So we all know the relevance of lithological data from our mineral system. So they can either represent the source or they can represent the position environment. So after we digitize it, we can do a check to see the association, how well some of these lithologies, how well they correlate with the non-mineralization. And then from there, we could compute a similarity map because lithological data is categorical. It's not a continuous data, it's categorical. So, but we have to convert it from categorical into a continuous raster. So we're employing different methods to actually convert it. So yeah, I think it takes a little time, but I think it's fine. Okay, did I miss this? Okay. I don't think the other data will be more demanding compared to this. The other data may be less demanding in terms of developing them. So I beg for your patience.
Hello, Dr. Tende. Dr.
Yes,
Tende,
sir.
while you are digitizing, can you
Yes.
take a small question?
Yes, no problem.
Okay.
Hello, sir. I'm worried about
Yes.
the labor of digitizing the map. What if you obtain the soft copy of that map and then crop the area that you need? Is it not possible?
I I need the area in shapefile. I don't have the shapefile. I need the
Okay.
area in shapefile because I have to assign weightings to this map. So I need it in shapefile. So, and having it as raster data is not tenable. We can't use that raster. We must use the first as shapefile to manipulate it before translating into a raster value. Is it okay? Sorry, have I answered the question?
Yes, thank you.
Okay, okay. If I had it as shapefile, I'll just crop it. But because there's no shapefile available, then I have to go through the process of digitization.
Yes.
Okay, yeah, so okay. Okay. I think I've digitized the major lithologies apart from the quartz and which are concerned of the mass meta sediments. So I have this. The next thing we have to do is to label them. So
So, Dr. Tende,
Yes.
I believe you are making use of the Nigerian geological map on a scale of 1 in 2 million.
Yes.
Okay. A very small scale map. So so we are starting with an issue already. But
Of course, of course. Those are some of the peculiarities you have when it comes to prospectivity. But I think we can still use it because we're able to identify significant lithologies
okay, okay.
across
Yeah,
the
yeah,
different
you're right. You're right.
environments. So
You're right.
it's not really bad.
Yeah, okay.
Mhm. So I have that. So yeah. So I hope to identify the different lithological units. So for PDF. Okay. So I'll just try and correlate the lithologies. Mhm. Okay. So I have the different lithologies to be input there. OGU, so I could use just measure terminologies instead of being more specific. Maybe granite, migmatite, permit me. So, so this is OGU, granite. Okay, let me start with this OPG.
I think you have some schist there. The blue is schist.
Yes, yes, the blue is schist.
Okay.
Mhm. So we have, okay, let me identify this. Let me just try schist. Mhm. Um, this is migmatite. MG is migmatite nice or migmatite. Migmatitic nice. Okay. So I'm putting it here. Here. Well, again, pigmatite. So we have pigmatite. OGU. Let me just term that granite. OGU granite. Yeah. OGP. Mhm. having a small error here. So in that case, I'll merge them together. Okay, no problem. I can still put granite. So and then yeah, pegmatite. So mm, granite. Right, okay, granite. So
Hello. Please, for the benefit of the
yes, sir.
younger ones, Dr. Tande, we are just trying to talk to ourselves
Yes,
here.
sir.
You can continue with the digitization, don't worry. So, for the benefit of the younger
Okay.
ones, what Dr. Tande is trying to do is just trying to digitize the different lithology, and he's assigning the names to each of the lithology you see there. Like the OG is talking about the different granitic body we have there. There are different code for them. OGP, OG, OGU, SU, the schist, the undifferentiated schist, and so other lithology. So that's what he's trying to do. So ideally, if to say we have all those lithologies as shape 5, we will have moved a little bit faster. But we actually have some of those lithologies as shape files, but they are not available here. So the first thing we need to do is to get the geological map, identify the lithology, digitize them as shapefile before you can assign any of the values you want to assign to them. And ideally,
Thank
if
you,
we
sir.
have
Thank
a
you, sir.
map with a better scale, it will have been better, maybe 1 in 100 or 1 in 50,000 of Kujeshi 207. But the
Yes.
map we are having now is the map of the north central Nigeria, which combine about 7 different states, and the scale is quite big. So there will be some mismatch. The scale is quite small, so there will be some mismatch in some of those lithology. But actually, this is for learning. So if we are to do this, we can make use
Yes.
of a large scale map, like maybe 1 in 250, 1 in 100,000, or even the most the most appropriate that we have in the agency, 1 in 50,000. We can actually make use of it.
Yes, sir. Thank you so much. So we have the lithological map. So I will be taking off the background map. Um, so we have this already digitized. So we put this into category. So add the values. So we have all the different lithologies that have been digitized across the study area. So in this case now we can import and superimpose um, I think gold zones, the locations of gold mineralization. So we have this. So there are fewer deposits I have there. So in this case now, we don't really quite well understand the relationship between which lithological unit is associated with which mineralization. So we have to deduce this relationship. So this relationship will be deduced based on computing the relationship between the target data and the evidential data. So we have the target data, which are the known gold locations. we have the evidential data for us to actually deduce a relationship. So the first thing I will do here is I will try my best to convert this data from shapefile into raster data, and then I will extract where each of these files are located. So I'll do a conversion. So convert from to raster. So I use convert to raster. So I'm using this. Okay.
Hello, Dr. Tende.
Before I come to that.
What are you combating?
Yes.
Are you combating what are you combating?
Converting the shapefile, what I want to do, I'm converting the shapefile into raster to find out the relationship between mineralization and the various lithological units. Now, remember, we have these lithological units, but we don't know the favorability for each of these data sets. Okay. And the only way we can compute the favorability is to do a statistical computation to estimate the relationship between mineralization and the various lithological components.
Okay.
Yes. I could see, I have to convert it, even though I thought about harmonizing each of these data into one file, but converting them will harmonize it. So if I convert from the future data into raster data, so the lithological data sets okay. So I have this converted. So I can, so they have values from 1 to 5. So what I can do next is to assign weight of significance to each of these data sets. So I will simply extract there's a tool called extraction. So I will input this data set and then input the mining location. So if I check this data, I can see the future value here. So what I will do now, I copy this into Excel. So I have this. Then I have to come back here, and then I copy this data set with the different futures. Here. So these values represent these values here. So what I need to do is to compute the frequency. So enter that. Then comma. This, I close it, then I frequency. So these are the frequency of mineral association to each of these data sets. So this is frequency. So these are the frequency, but computing the frequency alone is not statistically significant. So in that case, now we have to compute what is known as the frequency ratio. The frequency ratio integrates this data set with the number of counts. These are the number of pixels. So for us to compute the frequency ratio, we have to sum this, and then you have to sum this. So the frequency ratio is equals to this divided by the total, which is 27, divided by this all over this. So frequency ratio helps to tell us how significant a given lithology is with respect to gold mineralization across the study area. So we can see that the granitic bodies have very high frequency ratio, schist relatively low, porphyroblastic gneiss also very high. So these frequency ratio values now are then translated back here. So they represent how significant every lithology is with respect to mineralization. So this is how we generate the lithological data.
Yeah, Dr. Tende.
Yes.
While we appreciate you so much, I will still want to
Yes.
remind you, please, while you are developing the short, what do you call it, tutorial, please,
Yes.
we want you to be putting the reasons why you are carrying a particular action, like now combating the,
Okay.
I mean, calculating the frequency value. You've just explained it to say how
Yes.
significant a particular lithology is to mineralization. So such things,
Yes.
if you assign weight, why are you doing
Yes.
that? So we'll want that reasons, please.
Okay.
Yes, yes, yes,
Okay.
yes.
Can I explain it here, or have I explained it? Can I explain it here?
No. While you are developing the something, you are explaining it. I know, but we just want it so that
Okay.
we don't lose here.
Okay.
Uh,
Okay. So that is how we develop frequency ratio. So for the frequency ratio, we have um, the various value. So um, it's let me assess something first. Sigma time. Okay. All right. So that's fine. So we have that. The next phase I'm going to go into is the structural data. For the structural data, we have two components of structural data. So we have a lineament density, and then we have a lineament distance. Yes, we have to generate this data. First of all, the first step is for us to generate the lineaments. And these lineaments are like regional structures that are derived from spatial data. So lineaments can be derived either from satellite data, such as Landsat, Aeromark, or it can be derived from how they call this thing. You can derive it from satellite data. Yes, you can derive it also from digital elevation model. You can derive from magnetic data. So I think because of the scale, I'll prefer using digital elevation model. So we can input the digital elevation model into this system and see the lineaments or see the structures that are present. So I've already obtained the digital elevation model. The digital elevation model can be obtained either if you have the global mapper software, you can get the digital elevation model. It's simple. So if you have this software, all you can do, first of all, you import the boundaries like this. You import the boundaries of the area you are interested in, and then you could use there's a tool there, online tool. You can go there and download it directly. So sorry, I have to select this. You select the area, use the online tool, go into the site, select it. Here you will see the coordinates where you have to download. So you have Dropbox, all this thing. You can come here, download within selected polygons, and then you click it, and then the lineaments appear. So something like that. But this for different area, not for the area we are working currently. This is our area. So that's how you download lineaments. Digital elevation model. You could still make use of the geological survey lineaments if you think they're reliable enough, or if you think they have a good accuracy. You could make use of the geological survey lineaments. Apart from that, if you don't want to make it, you can generate your own lineaments, and then from there you can tie them down to lineament density and other parameters you're interested in. So now I'm going to import my lineaments. First, I import it into the project area. So I have the project area. I'll just demonstrate the lineaments. So I import it. So we have here on this ArcGIS, we could see there are a lot of structures. So you can visualize it from here. Really pretty good. Yes, sir.
So, Dr. Tende, if I decide to make use of the digital elevation model to pick my lineament,
yes,
how do I take care of the deep-seated lineament?
The deep-seated lineaments, digital lineament is superficial, not deep-seated, but it's also a reflection of the deep-seated lineaments. That's the argument they give, because them is a geomorphological inclined data set, so it takes care of the deep-seated lineaments also. You may have problems when you are using satellite data, because you may have lineaments that are not of geological origin. That becomes a problem.
That is it. That is it. So
Yes,
are we
if
not
you
better
have
using magnetic
uh,
lineament?
we
Lineament
could still use
extracted from
magnetic
magnetic
lineament.
data.
We could still use magnetic lineaments, but most mineralizations are not deeply buried. I think they are mostly near surface,
Yeah.
which
Yeah.
makes the dam still being more favorable
More favor.
for
Okay.
for delineation of lineaments. Yes,
Okay.
you could still use it, but my worry about the magnetic lineament, why I didn't employ it here, is not that they are not good; they are very excellent. But let's consider the scale. If you're looking at the scale, we might miss some very detailed lineaments, which are supposed to be picked, which will be picked by the dam. They might be missed by the arrow mark. Except we widen the area. If we widen the area, then the aeromagnetic data becomes very, very interesting.
Well, is there no provision of making use of lineament from different sources, maybe from the DEM and also
You
as
can do
well
that,
as the
but that's a
magnetic
longer
lineament?
process.
That's wonderful.
I've worked on that. You have what they call lineament integration, where you
Yeah.
can derive lineaments from different sources,
Remote
and then you
sensing.
integrate them now into a common platform. But that's a longer process, and if I start doing that now, it's going to
The whole day.
it means the training is going to extend beyond the process time. We could
Exactly.
do that well. We could still extract lineaments from them. We can extract it from AeroMap. We could extract it from satellite data, and then we can integrate the lineament now to provide a comprehensive lineament map or a composite lineament map. I've done that. I've even published on that, so that's possible, sir.
It's okay. Thank you.
Yes. So I'm using um, we have the digital elevation model. So I can extract the lineaments from this ArcGIS, but I prefer, because of flexibility, I like to use Global Mapper. It's more flexible for linear extraction. It has more representative, how can I put it? The resolution of Global Mapper is excellent compared to this. So go back to Global Mapper. So I have my Global Mapper here. Let me make use of this. So we have this. So this is the Global Mapper software. So we can see so we have linear features here.
Very good.
So we have linear features there, so we can start to extract them. Mindful of this, if you access this, you can see these are not I think these are not geological lineaments, these are roads. So we have to be a little bit careful. Just want to change the color to distinguish it. So
Hey, Dr. Tande,
Yes, sir.
please, is there no provision for automatic generation of most of those lineaments?
Automatic lineament is excellent, but you have the problem of automatic lineament picking non-geological lineaments also.
We know,
I could
but
run that.
you know,
Yes.
and I think another thing is when trying to extract such lineament, maybe we should
Yes.
have the administrative or utilities map on the background, less opaque roads and some other artificial things that may appear like lineament. Maybe that would be
Okay.
helpful. Maybe if we
Yes.
generate it automatically, we can out overlay it on maybe utility maps and administrative maps so that things like roads, power
Mhm.
lines, railway
Yes.
lines, we can actually extract them
Yes.
from the the one we did automatically.
Yes.
Because
That is true. You are right. It can be done automatically. You can do it manually. Um, well, I think whether I'm doing it automatically or manually, it still amounts to the same thing. But one of the defects about using automatic lineaments is you have to know the required threshold because you'll be having a lot of non-geological factors, not only roads, but also drainages that are not significant, that are not lineaments. They also show up as lineaments. So it's time consuming for you to actually start deleting those errors. I think it's better for me to just extract them manually, and then after I do a manual extraction, I just convert it into this thing rather than doing the automatic process, which is fast, it's easier. Yeah, it's fast and easier, but at the end of the day, you have to start deleting non-geological lineaments. You might miss out on some things when you are deleting, or maybe you may delete some configurations, or maybe there are some minute drainage network that may not show up, may not be very visible. So that makes it problematic now. How do you deal with such things?
so, okay, thank you, sir.
Okay. Actually, manual extraction is based on experience. So if you're well experienced, you can do the manual extraction. If not, then you can sort out the automatic linear extraction. But one of the things about the automatic linear extraction is sometimes it gives me curvilinear features. It may have some features that are not actually not vertical, or they're actually vertical, but the automatic lineament may be pointing out to be maybe a curvilinear feature, which is wrong. So it all depends on how well you assess it. If you can assess your lineaments, well, fine. If you can do the manual extraction very well, then you can go for the manual extraction. But if you're not too confident about the manual extraction, then you can go for the automatic lineament extraction. At the end of the day, we are looking for reliability. And anywhere you assess your reliability, then I think it's good. Except you have another alternative or you have another suggestion, sir. I think I welcome that. The best lineament approach is the composite, where you have to combine both lineament extraction from different sources. You could actually develop a composite lineament map which incorporates data because there are limitations to every data. We may have aeromagnetic data now. We may have satellite data. We may have gravity and all those things. Each of them are best at certain levels. So if we can develop a composite lineament map, then that makes it easier for us to actually have a more accurate lineament. Using one data, not really too good. I don't think it's recommended. But the only reason why I can't really do composite at the moment is because of time constraint. So I try to pick out the lineaments manually. I hope you excuse me for that. Um, and next time I'm going to try my best to develop a more composite map. I didn't want to just develop the lineament map and then come present it as lineament. I wanted to actually extract every feature myself.
No,
And
we,
then
we understand, Dr. Tendi.
yes,
Yes,
I
that's the
wanted to
best.
show
Yes,
how
yes.
everything is done.
That's the best way for learning. Demonstration. Thank you.
Thank you, sir.
The resolution of the global MAFA is quite good. Really, really good.
Yes, that's why I prefer using it because it's better than ArcGIS. You can see on ArcGIS, certain details will be missed out.
Prof.
But yes, but here
Yes, yes.
I'm picking out more detailed maps. So I'm sorry I'm slow, but I just want to do the right thing.
Yeah.
Yes.
Yeah, Dr. Tende. Hello, Dr.
Yes.
Tende. So,
I can hear you, sir.
yes, now you are extracting the lineament. So,
Yes.
so I'm just thinking, suppose,
Mhm.
suppose I have occurrence mineral occurrence map
Yes.
over this area. Then
Yes.
I now superimpose the occurrence map before extraction.
No, no, no. You'll be biased.
Oh, really?
Yes. The human mind is biased. If I
No, no.
superimpose it, I
What
will be
what I'm
biased.
saying,
I
what
don't want
I'm
to work.
saying is, if I superimpose the occurrence map, that will now
Yes.
control. It will guide me to which mineral has more which lineament has more frequency of occurrence. Then that's the lineament that I will pick.
Which direction has more frequency of occurrence? But superimposing it is crazy because you may end up seeing things you don't want to see. You may end up seeing an area like, okay, forcing yourself, being biased. Oh, this area. No, I want to see a lot of lineaments here to justify certain things.
Okay.
So for me to be less biased and to be neutral in terms of my lineament extraction, I prefer doing the extraction before superimposing.
Oh,
That
okay.
that helps my judgment.
Oh, okay.
But if
Okay.
I impose it, the area where I have mineralization, I will start forcing it. Or
Hmm.
maybe you start seeing more lineaments from that direction, which is generally not
Yes.
good
Yes.
for your
Yeah.
accuracy.
Yeah. I think I agree. Yeah.
Mm, yeah. Okay. I think so. I'm trying to trying to avoid. Okay. Mhm. So it's a lineament here. Okay. So yeah, we have lineaments here. I think I can go with this. Um, this routes. Okay. Think, okay, I can extract everything, but let's try to extract the measure linear mesh. So I have this. Um, color. Like so. Linear main has been extracted, so I'm saving them back. Structure, so generate on that folder of the exploration data set, and I'll title linear main map. So I have that. So I have that as a linear main map. Then here, after generation of the linear mains, I could do the next one is remote sensing data. So for remote sensing data sets, I'll be generating clay, ferric, and ferrous ion alteration. So this clay, ferric, and ferrous ion alteration, they represent different components of the mineral system. I think the ferric and ferrous represent their position, and then I think the clay should represent transport. So for this clay, ferric, and ferrous ion alteration, I'll be using Landsat data. Landsat data. So we have Landsat data. I'm using Landsat data. So here's my Landsat data, and this Landsat data is obtained from Ed Explorer website. So download it from the Ed Explorer website. So after downloading it, I have to extract it from the I have to extract it from the file. After extract it, it's impossible for me to use the NV data to actually import it on NV, because it has a meta file, something like a meta file that prevents NV from extracting it. Normally, I'm supposed to import into NV software, and then from NV software, I can then process it using normally I'm supposed to import it, but if I use the NV, it doesn't really go. It won't import, so it becomes a problem. So in this case, I have to group this the files using QGIS. There's a process of importing into NV, but that's more complex, and I don't want to go through that route because it's going to bring a lot of complication. So the best I'll do is I'll use the QGIS software to import it. And for the QGIS, I'll take raster file, and then I'll take miscellaneous. Then I'll take build raster data. So for the raster data now, number of input files selected. So I'm going to import add files. So I move to that database, and I'll add from band 1 to 7, 2, 3, 4, 5, 6, 7. So I'm adding from band 1 to 7. Click OK. Then I will click place each file into separate file. Then I can just click OK to run and build a virtual raster. So while it runs, it builds up a virtual raster, which is what I have here. So from here, I can export this virtual raster now as JOT format. Um, so you can just call it UJ. So I can export it into JOT. So it's been exported now. So now that it's exported into QJ, so I can take my MV, open image file. Can open it here. So I have the different bands. Okay, I don't know where the error is coming from. Let me attempt it again. Okay. So it's fine. So I have this. So I need to subset. I need to subset this area. I need to subset it from the satellite data. So I need to subset it here. So what I'm going to do now is I'm going to go back to where we have the boundary location. So I import it into MV. So I'll open it as vector file. So put it here, upon it, import it here. So from this layer, I would convert everything to ROI, choose the QJ, convert it. Then I'll subset it now. So I have this. This is the area under investigation. So this is it here. So because I have this, I can save this file. I can retitle it maybe QJ file or QJ area, QJ sheets. Save it. So normally we're supposed to do some kind of corrections, radiometric and geometric corrections for this data, which is commonly applied. So we could apply some corrections or maybe dark objects, all those things. But from what I've done over time, I just realized that those corrections, especially when you're dealing with predictive modeling, there are different ways we could do it. So I'll perform the quick atmospheric correction. Okay, does it have metal? Let me see. Okay, I'm supposed to input the different wavelength into the bands. That's why the quick atmospheric correction is not taking place. So I'll do dark object subtraction. So using minimal. So after I've done my dark object subtraction, there's need for me to do the atmospheric correction, which I've not done, but hello.
Hello.
Yes, so
Dr.
this for
Tendi.
me to do the atmospheric correction.
Why do you need
I
to do
think
that?
to correct for atmospheric defects, but because this area is within north central Nigeria, doesn't have severe weather problem, I don't
Yeah.
think that will be significant because in cases where we have in tropical areas like in the south where weather climatic conditions are very, very harsh, you need to do atmospheric corrections for these bands. But here, I think the atmosphere or the environment is somehow semi-arid, so that may not be problematic. So from there, we can perform band ratio. So usually there are different band ratios that we have where we could map clay, ferric, and ferrous ion alteration. So for the clay alteration, we can map it using band ratio 6/7. Then for the ferric, 6/5. And then for ferrous is 6/5, and then ferric is 4/2. So these band ratios gives us the spatial distribution of clay, ferric, and ferrous ion alteration across the area. So if I put it on this map and I'm developing a false color composite, so we can have it here 6/7, 6/5, 4/2. So we can have a view of the zones where we have clay, where we have ferric, and where we have ferrous ion alteration across the study area. So these maps, we have to impose export them individually. So for example, we have 6/7. So this is where we have 6/7. These are the high clay zones here. So I'll put this as alteration data. So we have clays, most of them down here, we have clay zones. So then we have ferrous. They have ferric. So that's how we prepare our alteration data. So we have that. input remote sensing data into my model. So we have them here. So the last data set we'll be dealing with is the geophysical data set. So for the geophysics, we have uranium on thorium ratio, we have analytical signal. The analytical signal will facilitate edge dictation and lithological contacts, while the uranium thorium ratio helps to map alteration zones. So start by developing uranium on thorium ratio. In this case, we are using OASIS Montage. I'm using a relative old version of OASIS Montage, or using OASIS Montage. So this is what I'm using. So I'll be here I have geophysics data. So I'm extracting it. Okay. So I have the radiometric data set. So this is it. So I'll develop uranium and thorium ratio. Oh, now this data is problematic. Anyway, I don't know, but I'll see at the end of the day because I don't have some section of the data, so that becomes a problem.
Is it part of the FCT build-up area that is the blank there?
I think so.
I think so.
Yeah, I think so.
I think so. Yeah, yeah. That
Yes.
that portion
Yeah,
was
so-
not blown, of course,
Yes.
for obvious reasons. Yes.
I think so. That makes us now.
Yeah.
We have to.
Thank you.
I don't know whether I should include this data into my model. Yes, yes. Because it's going to complicate a lot of things and introduce a lot of uncertainty. Except I have to subset this area, but I will just demonstrate how it works and the reasons why we have to include the radiometric data, because an important component, especially when dealing with goal mineralization. You know, uranium thorium ratio has an effect on mobilization. I think in sulfide areas are rich in sulfides, they present a more reducing environment for precipitation of gold, and that precipitation is clearly indicated by the uranium and thorium ratio. So I don't know whether to include this, but I will decide maybe or maybe not. Let's see. So I'm going to do grid band ratio here. So we have utilities, sorry, expression. Boolean operation, no. Sorry, let me just look for it to move, subtract, multiply, ratio grid. So we use for this option they call ratio grid and numerator. So we input uranium, denominator, input thorium output, so we can output this as KTH. KTH. I can't use K on TH because the software won't allow me, so I'm using just KTH. So gives me this map. So from here, there's always a problem importing this grid map into ArcGIS. It's always problematic when you import grid maps into ArcGIS. For example, now I'm having grid map here. So if I try to import it here, it becomes problematic. It won't go. But if you have the higher version of OS's montage, it's possible. But for this version, no. So what I do to convert it now into shapefile is I use an option convert. Can still be done on the higher version. There's an option here they call convert. So I use KTH here. So KTH yep. So we can use ERS. So yeah. So I have KTH and ERS. So back here. So I have them there. Sorry, significant proportion of the mineralization will not be represented here. So I'm sorry, I can't use this map because if I use it means that I cannot even employ my I can't employ machine learning because these mineralization types here are going to disappear and I want to use them. But I'm just doing this for demonstration purposes, also just to illustrate that the K on TH map remains important aspect of the mineral predictive modeling. The same thing too should be done also. I think if I have to import the aeromagnetic data, yeah, it's also going to give me, okay, this is a little bit better. So okay.
What is this? Is it the TMI?
Yes, the TMI.
Then what of the grid before it? Is it the one video or what?
Which of them?
The grid that is having some dummies, some blank.
Okay, that's the radiometric data set.
Oh, radiometric. Oh.
Yes. The radiometric, I don't think it lacks part of the this. So
but how is that
can't
possible?
really use it. Huh?
I'm just thinking. If you have a complete grid on the magnetic, then the radiometric should also be complete because they are acquired at the same time.
So I don't know. I can't explain it.
It's okay.
I can't really explain.
It's okay.
Can't explain it. I'm sorry. Yeah. I can't really explain it.
Yeah.
So should I ignore the radiometric, right?
Yes.
Yes, because it's going to introduce level of uncertainty. So we can't do it for this area.
Okay. Dr. Tinde.
Yes.
My colleague was just making clarification that the magnetic was actually interpolated. That portion really does not have data yet.
If it's interpolated, that means we can't even use the magnetic too. Because yes, we can't use it.
Yeah, you can't use it. You can't use it, yeah.
Yes. But anyway, in the magnetic, you can choose between, let me just put it because it's simple. Even though I'm not integrating it, I'm just trying to explain why we use the magnetic. The analytical signal shows us lithological boundaries and also structural data. We could also use the first vertical derivative for geological structures. So any of the magnetic data processing is important based on how you identify or how you relate it to the mineral system. So when you can't relate it to the mineral system, then it enables us now to be able to know why that data is being imputed into the model. I don't know if I'm clear on that.
Yes, you are.
Yeah, so despite the fact that we are not using this data, they still remain viable. If we had the complete data set, then we should have implemented them or included them into the model. So anybody that's undertaking this task in the future should enable to incorporate them into the model. I'm sorry I can't do them now because it's going to introduce a lot of uncertainty, a lot of error into my model, so I don't want to do it. So I'm sorry about that. But I hope you guys will excuse me so that we can move on. Am I excused?
You are. In fact, there's nothing you can do
Okay, so
about it.
thank you so much. Yeah, so I'm sorry, the geophysical data has to go. So I'm left with the lithological structure and the homosensing data set. So now in this data set, we have these components. We have the lithology, we have the ferrous, ferric, iron, and clay. What we need to understand is okay, let me go back to my slides. We need to understand the processing. We have done the processing now, but some of this processing are incomplete. For example, the lineament data is incomplete. And you can see why I said the biasing of the lineaments. You see, I deliberately refuse to. Now, when I superimpose this, you can see that there's still some lineaments here, the DEM fail to extract. Are we on the same page, sir?
You said the
Hello?
dam failed to extract.
That's why there's always the need to use multi-data type for lineament extraction. You can see that if we look at satellite data, there are more lineaments we didn't extract from the digital elevation model, but satellite data is showing us more lineaments compared to what we extracted from the lineaments.
Yes.
Which I clearly agree with what the prof said, that there's need for us to integrate different data sets to extract lineaments from the study area.
Yes.
Yes. So we could see add this up. Those lineaments we failed to pick up from the dam. You could still come here, you add it up. But anyway, I'm trying to avoid this because I am trying to avoid being biased. But in the case where we have lineaments that are clearly visible, we can't avoid them. For example, in this place, we can't avoid this lineament. It's clearly visible. There's no way you can avoid that. There's no way you can avoid this also. They are clearly visible lineaments, which we can't avoid them. Even here, there's no way we can avoid this lineament. This lineament is very conspicuous, even this. So there are other lineaments here. You can see this one too is also clearly visible. So there are some lineaments that are visible on satellite data, but on them, it becomes not visible. So you could support your lineament extraction using a multi-lineament generation. You could extract it using a variety of different data types. You could still assess them after you've extracted them to see how reliable they are. There are lots of lineaments, but when I superimpose my data, and then my mineralization, and I start extracting them, I become so biased. And in that case, I have to only extract lineaments that are clearly visible or well represented. So that's what I've done. So in this case now, what I will do, I have to start preparing the data for integration, which is the last step. So now the first thing I have to do is to check the projection of each of these data sets. And for you to have a distance-based projection, we need to have it represented in the UTM format. So I need to know the UTM format for Kuje, whether it's zone 32 or zone 31. So here I can use ChatGPT to check. So I can say
it's 32.
UTM. Okay, it's 32. Okay. So you can see check. So now
Dr.
we have
Pemi.
different data sets here.
Dr. 32.
Hello, sir.
Yeah, it's 32.
is on 32. So now, if I'm checking it, this check the projection for each of these data sets, I can see that, let me just check. This is in geographic coordinates, not in the projected coordinates. If I check this, also, this is more of the geographic coordinates. So it's not good. So if I check this, so I have, okay. This is 32. This is in UTM. And I guess for the rest of the data sets, so UTM, except for the lithological and the structural data sets. So what's important is for me to consider two things before I proceed into integration. One, I should be able to unify the projection. And two, I should be able to unify the spatial resolution of this data set. There are different ways you could actually unify, you could select the best spatial resolution, but normally the best recommended is the spatial resolution of Landsat, which is 30-meter resolution. So what I'm going to do is I'm going to convert an illustrative data into a 30-meter resolution while maintaining a UTM projection. So that helps to reduce disparity in terms of spatial resolution and also the disparity associated with the projection system. So for the ferrous, ferric, and clay alterations, they are all in UTM coordinates and they have a 30-meter spatial resolution. So I will start by reprojecting this data, the lineament data. So I will reproject the lineament data first. So I come to ArcGIS. So I come to ArcGIS and then I type reproject. So I have data. Sorry, my system is slow. Okay, so I input the lineament data and the coordinates is in geographic. So I'm inputting it back into UTM. Okay. So So because I have the projected lineament, I no longer need this. So I can remove this and I can just tie to this lineament. So from this lineament map, I'm generating two data types. The first map I'll generate, the first one I'll generate is the lineament density. Okay, so it's probably the name here. It's long, so let me just use line. Okay, so it's now output here 221, so I'll convert it to 30. Then I'll constrain the lineament density to the coordinates location on this tab. So I'm going to use the boundaries to constrain the extent. And this should also here, constrain it here too. So Okay, so I have this as the lineament density, line density. Okay, the next thing I'm going to generate is the distance to lineaments. But there's something I have to be clear here. It is more accurate if we actually know the direction of control for mineralization, so that we extract just that direction and how can I put it? You extract the direction and then you generate a lineament buffer data. But because the lineament buffering or the control, the line, the directional control for mineralization is not clear, even though visually I can see we have the north, east, southwest. Most lineaments are associated with north, east, southwest. I don't want to assume until I'm able to prove that statistically. I would generally extract lineament buffer for the entire lineament population. But when you're working in a scenario when you know the control for mineralization, it is advisable for you to extract that direction for mineralization and then generate a buffer. So this thing I'm doing now introduces a lot of uncertainty into my data set, because I'm also incorporating lineaments that are not supposed to, that are not primary control for mineralization in this location. I don't know if I'm clear on that.
You are clear, Dr. Tendi, but I also want to ask you a question.
Yes.
Now, we know that POLD is another major host of mineralization, especially at the POLD nose. So, where is the place of POLD in taking the mineralization source? Since we are dealing with lines now, how about POLD? Is POLD group under lithology? POLD.
Pole?
Yeah. Polding.
Fold.
Yeah,
okay, yes. Yeah, that could also be generated as an independent data set. Okay. You could generate the fractures differently, and then you could generate the folds differently also as another data set. You must not incorporate them within the fracture data set.
Okay, thank you.
Yes, you must not incorporate them. You could still generate them. In some cases, I've seen people generating measure lineaments or measure shear zones and extracting them, and also developing evidential layers for those data sets. It doesn't restrict you. The fact that I'm using lineaments here doesn't stop you from using them. So if you have the data where you can reliably extract data or fold data sets within this area, then you can go ahead and do that and then generate another data from that one and then incorporate it into your model too.
I have a question.
Yes, I am listening, sir.
Why do you have to introduce those lineaments that cause uncertainties?
Okay, number one, the directionality of the lineament here is not clearly defined, except I have to use statistical methods to define it. But if we know it, then fine, I can extract it. If I say, okay, let me say, let me assume, even though I have not, how they call it, I have not proven it, that the north, east, southwest lineaments are the major structural control, isn't it?
Yes.
That means that I will extract the north, east, southwest lineaments and use them as the structural control for mineralization in this area. So thereby reducing the uncertainty. That can still be done. Is it fine?
I'm still not clear. No, why you have to introduce linear? Why do you bother yourself with the lineaments that will cause uncertainty?
Okay, the explanation I have for that is southwest lineaments and develop a buffer map for that one. But because we are not sure or we are not clear about which of the directions are the major structural control for mineralization, that's why I am introducing a buffer map for the entire area. But if you're working in a familiar terrain where you clearly know the direction of mineralization, it's advisable for you to extract the lineaments for that direction and
Okay.
generate a buffer for it.
Okay, thank you.
Yes. If you're not sure in prospectivity, it's better you eliminate the data set. Don't force it. Every data set you input, you must know the contribution of that data set into the model. Is it okay, sir?
Yes, sir. Thank you, sir.
Okay. So if I assume, for example, here that the north, east, southwest are the major structural control, isn't it? I can extract them.
That's all right.
Should I extract them or should I just generate for the whole lineament area? I want you both to give me the go ahead. Yeah, I want to so that we should be satisfied. Everybody should be satisfied.
Yeah. I think
Okay.
we are okay if you consider just lineament in the northeast southwest direction.
Okay, so let me consider it. There's a process for me to do that.
Isn't it?
So the first thing I will do, I'll calculate the orientation. So x1 So this x and y, I have imputed. This column starts from the start and end coordinate of the different lineaments. So I'm trying to extract the orientation so that I should be able to know the north, east, southwest lineaments. So for me to do that, I need to calculate the orientation of every lineament here, and then use it now to extract just the north, east, southwest lineaments. So for me to do that, I have to calculate the start and the end coordinates of every lineament. And for the start coordinates, I'm using x, calculate geometry. So I'll take the x of line start. Then I'll take these. Y coordinate of line start. X coordinate of line end. Calculate geometry, the Y coordinate of line N. So I decided to maintain my coordinate output as meters. So after doing that, let me just go back to my data site file and input here. Not here. Okay. Lineament orientation. So export this. So for me to generate the actual lineament trends, I use a software known as Logwork. So I can add more columns. So I have this. We could check for the lineament properties, 2-dimension properties. So here we fit in x1, here we fit in y1, we fit in x2, y2, outputs bearing 2, 3, 4, 5. So the bearings comes here and the rest of this thing. So we have x1, y1, x2, y2. We have the bearings, we have the length will be imputed into the second column, and then the midpoints of x and y will be into the fourth and the fifth column to process it. So UTM coordinates, so you have to define it, automatic projected. So I have the bearings, these are the bearings. So these are the bearings for the various lineaments that has been extracted. So I will copy them back. Set them into editing mode. So then open it. Okay, so yeah, these are the bearings I have. Okay. So what I will do next is I'll save them. Stop. So the next thing we have to do is to identify which direction, which range of direction is not east, south, west. So if we're using paint, let me assume I have this. If I take this is the north, sorry. This is the north. This is the south, this is the west, and this is the east. So we know that this is 0, 0. This is 180. This is 90, and this is 270. So the lineaments that should be northeast should be somewhere here. Let me say 45. Half of this, but this 45 has a range. We should assume it is northeast. So we can say that, okay, 45 minus 22.5, to consider for northeast, I don't know, but I can just try and calculate it. If I take 45, that gives me 22.5 here, 0.5, and then 45 plus that's 67.5. 0.5. But we know that this direction also continues here. Some lineaments will also read in the negative angle, which means that if we take this direction plus 180, am I right? 22.5.
Yes.
180. So we have 202.
2.5.
Yeah, 202.5. So 202.5. Sorry. I need to put it down on sorry, let me just put it down well. So we have oh, sorry, to go back. So we have 202.5 here. So if we take from this other direction, if we take 67.5 plus 180, we have 247. Oh. Sorry, this 202 is supposed to be here. This 202. Yeah, for this 22.5. And then we take here, it's supposed to be 247.5.
Yes.
So these are the coordinate extent we're using to extract our coordinate, our north east south west lineaments. But we have to be careful because while extracting, we have to look at the lineament directions, whether those coordinates actually extracted the north east south west lineament direction. So I'll come here, I remove it here. I'm going to come here and I'll take select by attributes. Yes. So select by attribute. So from our map. Sorry. So the northeast south lineaments are greater than 22.5 but lesser than 67.5. That's the condition. So we say orientation is greater than equals to 22.5 and orientation is lesser, or let me say just say equal to or lesser than 67.5. We can do a check to see, verify, yes. So we can apply it. You can see that you can see. But remember, we have the negative angles too, not just this. All right?
Yes.
We have the negative angles. So we are going to use the negative angles. We are not stopping there. So we go back to select by attributes. So we take O or condition, orientation. Orientation is what is this something? So here we have what? So we have is greater than 202.5 and lesser than 247.5. Is greater than equals to 202.5 and orientation is less than
24.7.
Is it 24?
Yeah, 247.
267.5. Is it 267?
247. 247.
Oh, 247.5, yeah. So 247.5. So we also extract this. So now we are sure that the northeast southwest lineaments have been diligently extracted. But if you look at, we can still extend the range if you're not too sure. Like you can see, we have here, which means that there are some our configuration is definitely out of the range, or maybe this one is too how do I put it? It deviates more out of the northeast, so you can exchange the range to also incorporate these lineaments here. So if I have to extend it to be sure that those lineaments are also incorporated, that means the 222.5 to 67.5 may not be feasible. So I may extend it also.
Maybe from 20 to 70.
Hello, sir.
I say up to 75. Maybe from 20 to 70 or 75.
Okay, so this becomes what? 25 to 75. So if I put that here, okay, so I'm putting it here. 22.5 to 75. Can I put 70?
Yes, or we can make it 20 to 70.
Okay, 20 to 70.
20 to 70, that's 50 degree. Listen.
Yeah. So 20 here plus 180. So 200. +180. 250. So I've also extended it and it shows that it has to go more than that. So 75, 255. No, that's too much. Sorry, I have to do a check for these lineaments. The ones that didn't meet the condition. So you see, 16 degrees. 195. Sir? Yeah, why is 16 degrees? It's approximately 16 degrees. That means that I have to bring it downwards to incorporate those lineaments there. Yes.
So maybe we make it from 15 to 75, as Prof suggested.
Yes. Select my attributes. So, oh, okay. So, orientation is so it's greater than 15, and orientation is less than 75. Yeah. '75. I think this is fine now.
What of the reverse bearing?
He picked out all the north, east, south, west. Okay, so O orientation. So
That's
15 plus
195. That would be 195 to
Okay.
255.
And 2
55. The reverse bearing.
no.
The back bearing.
Okay.
195 to 255.
No. 70 plus 180. 250.
75, 75. It should be 75. It should be
No, I put
255.
75. This is 250, sir. 195. Okay, 195
5.
plus
The 15, the back bearing will be 195. While the 75, the back bearing will be 255.
50. This one 15 plus 180 gives us this. 70 plus 180 gives us 250. And the orientation
No,
is
75. We are using 75, not 70.
I use 75 and
Yes.
these lineaments here that are not north, east, south, west. Do you understand?
Yes.
When I use 75, see, you see, these ones are out of range. These are more of east uh, east of northeast lineaments. So when I put 70, it removes the east of northeast lineaments. So I'm more certain about the northwest southeast lineaments now.
What of those two lineaments are the northwestern part? It's not picking it.
No. These are not more of north. They are not more of northeast. These are more of east of northeast lineaments. Except you want me to incorporate them, but where I can put them 75. Because if you look at the orientation, this is, you can see here, that is more of this direction. I don't know if we are in agreement. Yes. I can hear you.
Yeah, what I'm saying is, 70 is also east of northeast. So,
Yes.
So you can still include 70, even up to 80, because see, there's another one there, but unless you are in, it's turning east-west now. But that's
I'm more interested in the northeast, southwest, not east of northeast.
northeast, southwest.
Southwest
That northeast,
yes.
southwest is 45. 45 is the exact northeast, southwest. East.
Usually, you can't get only lineaments that are 45. There's a degree of variability.
So moving. Okay, so 22 points. What you are saying now, 22 points away from 45, either below or above. Is that what you're saying?
Where the variability, fine, we can look at the variability, but you also have to look at the lineaments in terms of the way they are oriented on the map. Also.
Sure, okay.
Yes. We don't just do it blindly because of the figures. We also look at the way it's oriented on the map. And that's why I said when you bring it more to 75.
You focus on mineralization trend. Oh, it's okay.
I didn't hear you.
Yeah, so you are concentrating on the mineralization trend.
Yes,
vis-a-vis
the mineralization trend.
Vis-a-vis the lineament trend.
Yes.
Okay.
Yes. That's what I'm looking at. So if I put 75 here, it may end up extracting more to the east of northeast.
Yes,
because I'm also visualizing why I extract it. I'm not just using the figures. I'm also looking at the trends from the map also.
Okay.
Yes.
It's all right.
So if I put 70, I feel like, based on my own judgment, this is more to the east of northeast.
Yes.
So this one, I don't really want to consider it. I feel like it's more of east of northeast, not really like the others that are more of northeast. That is why I said 70 is too deviating from what I'm looking at the map. I don't know whether you understand me. Yes. And if I put the negative trend here, sorry, I can't hear you. Orientation.
Go ahead, Doc.
Greater than.
Go ahead, Dr. Tende.
If I put 15 plus 180. So if I take 15 plus 180, so this is 195. And orientation is less than 70 plus 180. 250. I don't think at this stage there's any new lineament. So I have mostly the northeast, southwest dominated lineament trends. So here, okay.
Maybe you still pick them.
Sir?
There are some lineaments at the southern part that appear to be more than 70.
This?
No, the other one. Go to your left.
Here? Here, okay. Means we still have to reduce the this thing, the orientation. But if those lineaments persist and we feel like they are out of range, there are two things you can do. You could deselect them. For example, I could just hold a control key and deselect them. If you don't want to deselect them, then means that we have to keep varying the ranges. So I've removed this thing. So anyway, I'll delete them. Let me just save this, then I'll remove them.
Dr.
So
Dr. Tende.
yes,
So
yes.
what is the implication of leaving the lineament instead of deselecting them? Why do you need to deselect them? You can leave them and just choose those that are oriented north, east, southwest. So
Yes, I'm coming to that. I want to. Okay, I'm coming to that. So I can then filter them out. So these ones are more of the northeast, but you see, this is not northeast, southwest visually. So I don't agree with that. It shows that the 70 I choose was greater. So these lineaments are the perceived northeast, southwest lineaments. So what I will do here is I will generate a buffer map for this area. So we have the northeast, southwest. So I will generate Euclidean. So I change the app resolution to 30. And then so I have yes. So I have a line buffer map, which shows me the distance from the lineament. The assumption is that the closer to the lineaments, the more favorable it is. The further it is, the away from the lineament, less favorable it is. So I have that. From the line buffer map, I have to come and reproject the lithological data, which has not been projected. The lithological data, I think it's more of the spatial reference is geographic. I have to convert it to projected. So we project. So output coordinates, I'm putting UTM. Zone 32. So this is lithology, but it's a mistake I made here. I didn't consider the spatial resolution of this data. So I have to still go back and reproject it because I'm considering all the spatial resolution of the various data sets to be 30 meters. So I will redo that again. So 30. So I can call this lithology, or let me just lithology. So I can take this off. I have the lithology, I have lineament buffer, I have lineament density, ferrous, ferric, clay. So that's fine. So this also should go. This also should go. So these are the various evidential data I have associated with my studies area. So the next thing we have to do now is to generate the target data. So I have to generate the target data. I have this, I have this, I have this, I have this data sets. So the next thing I'll do is to generate the target data sets. And as I earlier explained, the target data set consists of positive and negative labels. That is what the target data set consists of. It consists of positive labels and negative labels. The positive labels are the mineral deposit locations, which you already have. The negative labels are randomly generated points. Now, there's an intrigue into generating the negative labels. If we have to generate the negative levels across this area without any degree of restriction, we may end up seeing that certain locations or certain positive levels locations will also coincide with the negative level locations, which introduces a degree of error into our model. In order to avoid this, we have to perform or have to generate buffer around these positive levels so that when we are generating the negative levels, when you are generating negative levels, zones of the positive levels should not coincide with zones of the negative levels. So we have to do what we first of all perform Euclidean, and then we have to select an appropriate Euclidean distance, which will serve as buffering or the buffer distance. And different authors have proposed different distances. And some authors propose distances as of 1,000 meters away from the positive level. Some of them propose distance of 2,000 meters away from the positive levels. So we're going to see it. We're going to try the different buffer distances and then use those buffer distances now to generate the negative levels. So we perform the Euclidean. We perform the Euclidean analysis using the mining locations as the sample. I can put 30 meters here. And then I'll use this boundary to ensure that the Euclidean distance doesn't go beyond the coordinates of the boundary location. So we have that. So we have this. So different authors have proposed different buffer distances. Most favorable, some of them have talked about 2,000 meters. So we create a buffer of 2,000 meters. So we separate this into two classes. Then we create a buffer of 2,000 meters. This ensures that the positive levels, sorry, the negative levels are not created within zones of the positive levels. They are created out of the zones of the positive levels. So we have to create this buffer. So we convert this buffer now into two classes by reclassifying. So we could label either of them. Since I don't do this one, I put 0. This is optional, so it's not really important. Okay, I have this. So the 0 class are the zones where I don't want the negative levels, and the one zones where I want my negative level to overlie. So from this case now, we'll be able now to convert this into raster format. So we convert it into raster, sorry, into shapefile, not raster. So we convert it. So we go into Analytica tool, conversion or conversion tool. So from raster into polygon. So when we convert into raster, we can then remove the 0 file so that we can extract okay. So the reason why I did this was to make sure that the negative samples are constrained within these zones that demarcate as 0. They don't coincide with the zones where we have positive levels. So I have that as a negative levels. So from here, the random samples. So excuse me. So I have about 26 locations, 27 locations, 27 locations. So it means I'm creating a random sample of 27 locations. So you can title it random points. Constraining class, I will put this constraining class. And you could maybe specify number of points, field optional, and all these things are optional. So you could still configure them. Sorry, it's like these points are, I didn't select the number of points. Oh, it's wrongly done. I will beat it again. So the constraining class is this. The number of points we have is 27. Positive levels. So I have to put 27 negative levels too. So I think so. Yep. So I have these points are the negative labels, and these other points here are the positive labels. So in machine learning, we have both positive and negative labels. And usually for us to train our data set, we have to label each of these labels using quotes. For the positive labels, which are evidenced or demarcated by mineralization, we label them as 1. And for the negative labels, we label them as 0. So the positive and the negative labels in machine learning becomes what we call the dependent variables. Those are the actually statistical names. They are the dependent variables, while the other variables are known as the independent variables. So we can label this. We have to create a file here, add field. So I will just title dependent variable. And because I'm dealing with a random point, which is considered to be negative variable, I will say 0. So the quote we will give for the negative variable is 0. Then for the positive variables, which are the mining locations, I also add that field depending. And then the code I'll give for this is 1. So in some cases, you don't use 1 and 0. In some cases, we use yes or no. So it's still the same thing. So 1. So I have the dependent variable here, which are the positive labels as 1. I have the dependent variables, which are the negative 0 as these negative labels as 0. So what I'm going to do next is I'm going to merge both the positive and the negative labels. And the merging of both the positive and negative label becomes our training data set. So I'll put this here. So this is known as, sorry, not the training. This is the target data, which I earlier mentioned. So this is called the target data. And if we look at the field of the target data, we don't need other columns. We just need just this column. So I just need just this column. So it becomes my target data. So from this target data now, I would have to do predictions using this target data sets. And that will follow in the next couple of this. So before we leave, I'll extract. So input my target data here, which is the dependent variables. Then I'll input and extract the points, each point across the various data sets. So I have this. I have the different data sets here. These are the different data sets I have. So I'll copy this into Excel. Hello.
Hello, Dr. Tinde. We are with you.
Okay. So I copied it here. So this is the data set that we will use for prediction. So this will be saved. I will save it as let me just say data.
Yes.
So I'm saving it as data.
No.
Usually CSV. File is fine.
Whatever. Spreadsheet.
So,
Come on.
so this data set is what we use for machine learning predictions, and then translate it back into the spatial data. So we are predicting this. So we've extracted this data, and then this will be used for prediction. I think we can take a break, but before we take a break, I will first of all run collinearity analysis using variable inflation factor. There are different softwares we could actually use collinearity. One of the software you use, yes. This is just a 2 minutes. I know people are tired. My software is not even working, so I think we can take a break. Let me not keep people.
I think so. Please
Yes, so we can
appreciate-
take a break. It's okay.
Okay, thank you so much. Let's appreciate Dr. Tende. You're so wonderful, and we thank you for all this which you have delivered seamlessly to us. Thank you so much. So we take
Thank
a
you
break.
very much, sir.
Dr. Tende, like how many minutes would you want us to break?
I think we should our program schedule. I think this should be a lunch break. People need to take something. So I think I'll
So
ask
we'll be
people
back.
like, maybe,
We'll be back 3 o'clock. Is it?
4 o'clock is fine.
No, 4 is when we are.
Oh yeah, 3 o'clock.
well,
Sorry, 3 o'clock. Sorry, I'm 1 hour ahead of.
you're 1 hour ahead, yeah.
Of your own time. So I'm taking from my own time here. So
Okay,
3
okay,
o'clock is okay.
okay.
Yes.
Thank you. Another round of applause, please, for Dr. Tende. So we'll see you 3 o'clock, 4 o'clock your time. Thank you.
Thank you, sir.
Thank you.